In this example, we're going to look at how to write an equation for a line that goes through two specified points. I really like this example because I kind of see it as the universal example. This also is the way that linear equations arise in real life. If I have a relationship where I have two different data points, just two different observations, and I postulate that those quantities, x and y, are related by a linear equation, then this is how we get information usually from the real world. That now we're going to come up with a way to find an equation for this line using nothing more than these 2 points as the information that we're given. So what's our strategy going to be? Well, what do we know and what do we not know? In this example, we know the coordinates of 2 different points, but neither of those 2 points happen to be the y-intercept. And for that reason, the slope-intercept strategy is not, in my opinion, the most natural one to use. Now, a lot of students do still choose to use this strategy, so we're going to look at how it works. But I'll have a second strategy that I personally prefer a little bit more to look at second. So if we're going to use the first option, slope-intercept, the first thing we need to do is find the slope. And to do that, we're just going to take the 2 points that we know, measure their rise, measure their run, and then subtract. Well, what does it mean to measure a rise and a run? It means to subtract, respectively, the y-coordinates and the x-coordinates. And dividing those two differences by one another gives us this famous formula for slope, y2 minus y1 over x2 minus x1, meaning the y-coordinate of the second point minus the y-coordinate of the first point, that measures the rise, divided by the x-coordinate of the second point minus the x-coordinate of the first point, that gives us the run. Once we know the slope, we can pull out our template. And in slope-intercept, our template is y equals mx plus b. So if we know the slope, then we know that we can place that number into the equation as our value for m. But then that still doesn't tell us what b is. And this is the step that is the most clunky to do when we're choosing option 1. What we need to do is determine the intercept by using either of the 2 points x and y values that we already know. So that's the shape of how option 1 would look. Find the slope, throw it into y equals mx plus b, and then plug in one of the 2 points that you know to then you do some algebra and determine a value for b. There's a second option. And as I mentioned, this is the option I like a little bit better personally, but that's my own taste. The cost of admission to this option is to memorize or remember a different form for a linear equation besides y equals mx plus b. It's called the point slope form of an equation for a line. And as its name suggests, it's a valuable tool for finding an equation for a line if we know the slope and we know just some random point, which is not necessarily the intercept. The strategy starts the same way, by finding the slope of the line by dividing the rise by the run. But then, here's the nice part, rather than having to do some algebra to find a value for b in the slope-intercept format, what we're just going to do is place the slope that we find, as well as place either of the points that we know into what we call the point-slope form of an equation for a line, which looks like y minus y1 equals m times x minus x1. So it's a slightly different formula to remember than y equals mx plus b, but depending on your taste, it might be well worth it because the algebra that we had to do before, we might not have to do now. We might still want to do a little bit to simplify the equation that we end up with, but a lot of that too depends on what your professor expects or what your online system expects as an answer for the problem. And plus, the simplifying that you do here is often easier to do than the simplifying you would have to do using the slope-intercept approach. But I want to look at both strategies, keeping in mind that in both strategies, the first step is the same. So you don't even have to decide right off the bat which of these 2 approaches you want to use. The first thing you're always going to do in a linear equation problem, a problem that's asking you to find an equation for a linear function, the first step is always finding the slope. So let's do that. First of all, what are the coordinates of these 2 points that were given in the problem? Just looking up the x and y coordinates of these points on the axes that are given, -4, 3, and 1, 6 are the coordinates of these 2 points. So we need to use that information to find a slope. How do we do that? Well, let's compare these 2 points. Comparing their y values, the y value of the first point is 3 and the second point is 6. So if I go from the first point to the second point, I'm rising by 3 units. So I'm going to call that plus 3. Meanwhile, the x-coordinates go from -4 to 1, which is a difference of 5 units in the x direction. So we can think of our rise as plus 3 and our run as plus 5 on this graph. And just to connect that with a formula that you probably remember for how to compute a slope, y2 minus y1, 6 minus 3, and x2 minus x1, 1 minus negative 4. Those were exactly the calculations that we just talked our way through up on the graph paper. That 6 minus 3 gives us the 3, which is what we call the rise, the vertical difference between these 2 points. And the 1 minus negative 4 gives you positive 5. That's the run, the horizontal difference that connects these 2 points. The ratio of those two numbers, 3 divided by 5, is then the slope of this line. Well, great. That means if we're using the slope-intercept approach to finding an equation for this line, we now know that we can plug in 3/5 for the slope. Namely, in y equals mx plus b, we can replace m by 3/5. But what we don't know is we don't know b. So we can't finish our equation until we determine a value for that unknown constant, that b that's sitting out in the front, which happens to be the y-intercept of this line. So that's the remaining question that we have to answer. What is the y-intercept of this line so that we can place it in b and be done with our equation? Well, to find it, notice what we really have now is an equation that relates 3 unknowns together, x and y, which are the coordinates of points on our line, and b, which is our unknown y-intercept. So if I want to determine the value of any one of those unknowns, I have to specify the values for the other 2. And because I don't know b, my only option for what to do is to specify values for x and y. Those values can come from either of the 2 points that we know on our line. So for instance, if I want to choose, let's say 1, 6, I like using that because it's got positive coordinates. So I don't have to worry about making too many sign errors. That means I'm going to plug in a 1 for x and a 6 for y into my equation. So I get 6 equals 3/5 times 1 plus b. Now the only unknown that's left is b, which means we can solve this equation and get b by itself. 3/5 times 1 is equal to 3/5. So to get b by itself, all I need to do is subtract 3/5 from both sides. So b is equal to 6 minus 3/5. And now you pull on your fraction arithmetic hat. Remind yourself to subtract 6 minus 3/5. We need a common denominator between 6 over 1 and 3 over 5. The best choice for a common denominator here is 5. So we'll bring both fractions into denominators of 5. 3/5 is already there, but 6 over 1 we can bring into fifths by multiplying the numerator and denominator by 5, giving us 30/5. And then 30/5 minus 3/5 is 27/5. So b is equal to 27/5, and we've determined that unknown y-intercept. Often a lot of students will stop right here, and I always take off points because the original question asks you, write down an equation for this line. Finding b was not the point. Finding y was the point. Y equals something, 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 right? So if we want y equals mx plus b, we need to also put this value for b back into the equation and get y equals 3/5 x plus 27/5. There is a slope-intercept equation for this line. So taking option 1, the slope-intercept strategy, the first thing we needed to do was find the slope of this line, which we did by subtracting the y-coordinates to find the rise, 3, subtracting the x-coordinates to find the run, 5, and then dividing those 2 to get 3/5 for our slope. Placing that into the m of y equals mx plus b then gives us an equation whose only unknown quantity is the b. And to find it, we plugged in either of our 2 points, x and y, and then solved that equation for b. You can check that if we had chosen negative 4,3 instead of 1,6 to plug in right here, we would still get the same value for b. And that's going to be the case as long as we got our slope correct. So that was the slope-intercept approach. And the difficult part of the slope-intercept approach was doing this last step, determining the value for b. I also want to look at an approach that is a little bit more direct, that doesn't require us to do quite as much algebra, but which sort of has us remember a different form for a linear equation besides the slope-intercept form. So let's talk about option 2, that we call point slope. Option 2, again, begins with the same first step. The first step is always find the slope, and so if we did the same steps all over again, we'll still find that the slope of this line is 3/5. So picking the story up again, now it's step 2. What we're going to do, instead of using y equals mx plus b, is use this format of equation. Y minus y1 is equal to m times the quantity x minus x1. That's the point slope form of an equation for a line whose slope is m, and which passes through a point with coordinates x1, y1. So that's the great thing about this, is it can take any old point on this line, as well as the slope, to determine an equation straight away. The point that we choose does not have to be the y-intercept, b, har har. So we know the slope is 3/5, and we can directly then plug in, again, either of our 2 points as the x and y coordinates for this line. I'm going to choose 1,6 again, but again, we would end up in the same place no matter which of these 2 points that we chose, as long as the slope that we computed was correct. And so what point slope does for us is it shows us right now, here is an equation which describes this line, y minus 6 equals 3/5 times the quantity x minus 1. And depending on your professor's preferences, sometimes we can stop here. Just be done. I have my equation. I could use this equation if I wanted to determine other points on this line if I were so inclined to. And this, the hard work is mostly done. But just as an exercise, and just to make sure if your question happens to ask you for an equation in slope-intercept format, for example, or if your professor expects it, then what we can do with this equation is to solve it for y. So this is an optional step. We could stop here, but instead, let's just solve it for y, just to make sure that this method gave us the same answer, describes the same line as the method we used in option 1. So if I want to solve this for y, the first thing I might do is simplify the right-hand side by distributing the 3/5. 3/5 x minus 3/5. To get the y by itself, then I have only one more step to do, and that's add 6 to both sides. So y is equal to 3/5 x minus 3/5 plus 6. That's the same as plus 6 minus 3/5, which a minute ago we convinced ourselves was 27/5. So indeed, we end up with exactly the same equation as we had before, but in my opinion, the algebra that we had to do to get there was simpler, less fraught with potential disaster than using y equals mx plus b. So if you have room in your heart for one more equation to describe linear functions, make it point slope. Y minus y1 equals m times the quantity x minus x1. It's great because you can use it in any situation where you know the slope and any point on your line. Just plugging in that value for m, the slope, and plugging in x1 and y1, any point that you know, you immediately have all the sort of tricky bits done, and you have an equation for your line, from which, if you choose to, or if you're asked to do so, you can then solve it for y and get back to your slope-intercept format. But to me, this is a little bit lighter lifting than trying to make slope-intercept work in every situation.